Okay, my apologies for not being able to be in person, but unfortunately, my son looks like he might have COVID, and so I am hoping I'll know by tonight whether or not he tested positive. And if he tested negative, we'll be back in class on Friday. If he tested positive, then we're actually going to have to do video lectures for another week. But I wanted to go through a few things with you. And so the first thing that I want to do is just show you Blackboard. If you look in the week of 9/7, there'll be one more link here for this video, but you'll see that the homework has been posted. There's a quiz that opens at 8:30 on the 9th, so tomorrow morning, and I'll show you with that in a second. It has to be uploaded. I prefer the PDF format, but it needs to be uploaded no later than midnight on Wednesday. So you have all day with it, but it needs to be uploaded Wednesday. Then the worksheet that we will go through today, as well as the lecture. We don't do a lot of lecture slides. Most of it is going to be from the worksheet, but I just wanted to make sure that you had that content available to you. So let's look at the quiz. The quiz here, you see an individual borrows $25,000 with a plan to pay the 1% interest payment each of the 6 years and then pay the full amount at borrowed at the end of year 6. So that's the scenario. Paying interest only. So draw the cash flow diagram from the borrower's point of view and the lender's point of view. So borrower gets $25,000 and is paying 1% interest each year, full 6 years. Borrower, lender. Then you're going to calculate the total amount repaid to the lender that's using the repayment method listed above. Now we're going to assume that the borrower pays one lump sum at the end of year 6. You're going to calculate that, and you can calculate that either using the formula or you can calculate that using the compound interest tables. Either way is fine, but you're going to calculate that using the formula or the compound interest tables. And then question 5 is just the difference between the two. So the difference between 3 and 4, which one's bigger, which one's smaller, and why. So that is the quiz. 2 cash flow diagrams, total repaid to the lender if using the method stated above, total if you do one lump sum at the end of the year, the difference between those two methods. Very straightforward quiz. You have all day at your disposal. So we're going to launch in to the worksheet we were doing previously to look at finishing up future and present values using the compound interest tables and the formula. So we had drawn a cash flow diagram, and now we're just going to do a couple F&Ps. Now, we had, I think we had done these cash flow diagrams already in class. So I'm going to draw them quickly off to the side so that we remember we always have a cash flow diagram, but it's important for you to kind of track. We did have this in your previous notes, or at least you should. So we're going to share the camera. Oh, wrong camera. All right, there we go. I don't know why there's a little window of me as well, but what you really need is this big version of the worksheet. We're going to try to focus that a little more. Let's see. Focus. Well, that's just looking more and more fuzzy. Not sure why that's looking so fuzzy. It's certainly big enough, but it is. Sorry for this, guys. There we go. All right. That looks better. Okay, find the future value given a present value of $10,000, interest rate of 6%, and an N of 5 years. Use the formula, use the confidence, use the compound interest table. And so we're going to say that the present value, and because it wasn't stated explicitly, I'm just going to draw the present value as up at time 0. And so P equals 10,000. Actually, we're not drawing any arrows. I was just doing those as tick marks, but I don't really want any arrows. I'll have them cross the axis. 1, 2, 3, 4, 5, 6. So at time 6, there'll be a future value equal to an unknown amount, and the interest rate is 6%. Oh boy, I'm just really screwing up here on this video, aren't I? N is equal to 5, interest is equal to 6. Okay, so present value, $10,000, interest rate is 6%, N equals 5, 1, 2, 3, 4, 5, and we do not know what the future value is. We're going to solve for that. Cash flow diagram, done. Formula. Formula tells us that we have to find the future value. We are going to future value is equal to the present value times 1 plus I to the n. So that is equal to $10,000 times 1 plus 0.06 to the 5th. So if we multiply that out, you have $10,000 times 1.06 to the 5th. 1.06 to the 5th is equal to 1.338. So that becomes $10,000 times 1.338, which equals $13,382.26. So $13,382.26. Now I'm going to use the confidence, sorry, I keep saying confidence, thinking back to teaching statistics and economics. Now we're going to look at the compound interest table. So we see that F is equal to P times F of P, comma, I percentage, comma, N. So that means that we have $10,000 times the future given the present value times 6% at 5 years. You look on your table and you will see that that's 10,000 times 3.8. I have 13,380. Very much the same answer, whether I use the formula or I use the compound interest table. The present value, if I'm given the future value of 13,380, my interest is 6%, and my N equals 5, what's the present value? Well, we already know what it is, right? the formula, we're just doing the same problem as problem 6, but we're doing it backwards. But the formula is equal to, the present value is equal to the future value times 1 over 1 plus I to the n. Why? Because it's the inverse of the previous formula. So instead of p times 1 plus I to the n, we've got f times 1 over. So it's the inverse. We can also rewrite that because it's the inverse. We can also say that p is equal to f times 1 plus I to the negative n, because mathematically that is equivalent. So that means that we have $13,380 times 1 plus 0.06 to the negative 5. Plug that into your calculator and you'll get $13,380 times 0.74. If I'm trying to find the present, always be in values less than 1. When I'm finding a future value from a present, I should always be in values greater than 1. Why? Because time value of money as much as the future, or if you're given a future value, you're less. And so double check yourself with easy thing out, and you get $9,000.87. Well, what did we started with in problem 6? $10,000, so we're off by $1.13. That's okay. I can live with that. So must have hit something. Sorry about that. Let me zoom out a little bit. Okay, so using the compound interest table, we have that the present value is equal to the future value times the present value given the future value. So if you are trying to find the present value, the P comes first. If you're trying to find the future value, the F comes first. Those are just little tricks to help remember as you're doing this work. So present value, you have a future value given to you. So it's find the present given the future, or P of F, times I with I percentage over n number of years. That's our basic formula. And so we look at this and we say $13,380 times the P given F factor for 6% over 5 years. So you can see that the formulas for using the compound interest tables, the formulas are very, very similar. And that's why I said it's important for you to write down all of your steps when you're doing an exam, so that I know what you used for I, what you used for N, were you using an F of P factor or a P of F factor. Those are all things that are important when I'm grading, to make sure that I see that you understand how to approach the work. So we have $13,380, and from our compound interest table, we find that the value is 0.7473, exactly what we found from the formula above. So we get the exact same number, $9,998.87. So both of these examples, for the present given the future or the future given the present, just show you that you do have an algebraic expression that would create this, but our compound interest tables let us find this information quickly for any type of answer. Now, as we start looking at annuities, the equations become much more complicated, and we would never want to do those by hand. So while our P and F factors are pretty easy and the algebra isn't too intense, once we get more complicated scenarios, you're going to be really happy that you have those compound interest tables. And so I personally would just use compound interest tables for everything. But like I said on the quiz, you can use either the formula or the compound interest table. Either will work. So Then the final part says find the number of years required if you have your F and you have your P and you have your I. So this is the last formula I'm going to give you from this part of the chapter. And so we can find what N is if we take the logarithmic value of our F given P factor over the log value of 1 plus I. So that's your interest rate, right? That 1 plus I, that's that magic compounding interest rate. And so we have the log of 13,380 divided by 10,000 divided by the log of 1 plus 0.06. So this is equal to the log of 1.338 divided by log 1.06. And that gives you 4.997 years, or approximately 5. So one problem, and we've seen the relationship between the present value, the future value, the interest rate, and the number of years you're compounding. So that's the point of this worksheet, is to just show you that whichever way you come at it, backwards, forwards, or sideways, you're going to get the same numbers. So these formulas, that's why I said you can use multiple formulas to solve for a given value, depending on what basic information has been given to you. And so we start out with our present and future values, because those are the most straightforward algebraically, and we can see the relationship between the algebra and the compound interest table. But what we're moving into in the next sections are for annuities, or looking at continual amounts over a given period of years. So I'm going to switch sharing my screen to my PowerPoint file for you. And we're going to go back to these lecture slides. And so here we have just our F and our P. So if you have the P and you're looking for F, you use that 1 plus I to the N, or find F given P using a specific I and a specific N. If you have your future value and you want your present value, you're going to use the factor of the inverse, 1 over 1 plus I to the N. And our formula is P given F at a specific I and a specific N. So that's all what we were doing before. Now we're looking at an annuity. And an annuity, I've only added one letter to our previous listing, and that letter is A. It's the annual equivalent at the end of period 1 through N. Now, the important thing to note here is that the annual equivalent is at the end of period 1. It's always at the end of period 1. Why? Because we need to make sure that we know when our deposits and our withdrawals are happening. And as we talked about in our last lecture, face-to-face, we had a series of deposits and withdrawals. And if you have both of them happening at the same end of period, then you can credit yourself for the deposit, take away the withdrawal, and still just end up with a credit if the amounts balance out that way. So we've already looked once before at the cash flow diagram. We've done this in class, but you see that for each of the years, we have arrows going up with an A, and that amount given would be put either above or below those A's. We still just put the interest rate somewhere, and we either would have a present or a future, okay? We're not ever finding both. We're either going to be finding a present value given uniform amounts, or we're going to find a future value given uniform amounts. You will never find both, okay? So in a problem, we'll see the present or the future, an interest rate, and the number of interest periods. And the uniform amounts are at the end of those interest periods. Now, the last slide here, I actually have as a handout for you that I'll give to you next week in class or the next time I see you. And you'll see that once again, we have some examples of what it looks for to find a future value given an annuity, find a present value given an annuity, find the annuity given a future value, and find the annuity given a present value, and what each of those equivalent solutions are, and examples of the cash flow diagram, which I think are really helpful. So what we're going to do now is we're going to switch to the worksheet, and I'm going to work through these problems, not the ones that are on that slide there, but the problems from the worksheet. And so you can take notes as we go along, and we will only be using the compound interest table. The textbook will show you the algebraic equivalent. It gets pretty hairy pretty quick, and so we're only going to be looking at the compound interest formulas. So let me switch back to video. We'll see if it switches directly to video or if it, for some reason, goes to me. It went to me. That's not helpful. That's not helpful. There we go. That's the one we actually want. All right. So the first one says, if you save $730 per year, or the equivalent of $2 a day, for 35 years, how much money would you accumulate if the annual interest rate is 7%? And that's how much money would you accumulate over that 35-year span. Now, this first one gives us an example that we're not going to draw 35 little arrows. That's a lot of arrows. That seems unnecessary. So when I start out with the cash flow diagram, I am given a value for the annuity. I'm given an N of 35. I'm given an I of 7%. And what I'm looking at is how much money will I accumulate? So how much money will you accumulate? Future tense, so I'm looking for F. That is what matters here. So cash flow diagram. Because it's me, I'm going to think of it from my perspective and say, each of these deposits over 35 years are me putting money into an account. So that's A is equal to 730. But then at the end of all of that, N equals 35, I'm going to be able to withdraw some future amount because I'm saving at an interest rate of 7%. So you see, arrows are going down. I did not do and just drew a bunch. Finding a future. Well, my formula is that is equal annual times rate 35 years. Okay, so what I see is that I have $730. My F&A factor for 7% over 35 years is equal is equal to 8.237. Is unitless. So the $730 has a unit, dollars, but this is just a factor. It's a multiplier, so it has no units. So the only units I'm left with are dollars, and that is $100,913.01. All right, that's because I'm using the generic formula F is equal to A, F of A, I, N. That's the general formula. And then this value came from the compound interest table with an N of 35, looking at 7%, looking in the F given A column. And we'll look at these together again when we're in class. All right, so the next one, an improvement is made to a machine that gives you an extra cash flow of $20,000 at the end of each year for 5 years. If the interest rate is 15% per year, how much can you afford to invest in the improvement for the machine? So what am I given? I'm given A is equal to $20,000. I'm given N is equal to 5 years. I'm given I is equal to 15%. And what am I looking at? I'm looking at how much can I afford to invest? Well, that's what am I putting in now. So I'm going to find a present value. That's what I'm looking for. So my formula is after I do my cash flow diagram. So in the present, I'm going to invest. So I'm putting a down arrow because I'm making an investment, an unknown amount. That's what I'm going to find. Then over the next 5 years, 1, 2, 3, 5, I'm going to reap the benefit of an additional $20,000 in additional cash flow. And this is at an interest rate of 15%. So present value going down, question mark, because I'm trying to find it, but my cash flow, my extra cash is in the positive direction, $20,000 over the period of 5 years at 15% interest. So baseline formula to find the present value, P is equal to the annuity times the P given A factor, which is a factor of the interest percentage and the number of years N. So I'm going to multiply A by my value found in the compound interest table. So A, I'm looking at the P given A column. I'm looking at the 15% interest table, and I'm looking for an N is equal to 5. And so that means I have my $20,000 for my annualized amount multiplied by 3.352. That's the factor I found in the compound interest table at 15% for 5 years, finding the present given an annuity. Multiply that out, and I have a present value is equal to $67,040. So that means as an engineer, I could justify $67,040 to do an improvement because it's going to yield $20,000 every year over the next 5 years. Now, what if I was talking about something called ROI? What's my return on investment? Like, what's my 5-year return on investment in that? Well, I could say that I would have a break even, and we'll talk about this more in the future, but this is kind of an introduction to that because we're saying like, you know, I'm going to make this investment up front, but I will have earned back that money because of the improvement within 5 years. And then every year after the 5 years, I'm just going to make an extra $20,000. I'm just going to keep getting that extra cash flow, but I've already paid off my investment. Those are the types of decisions we use as an engineer to say which option is the best. All right, I did change this problem because the tables I uploaded didn't have an N of 45, so you need to change that to 50. But this one says a 50-year-old person wants to accumulate $750,000 by the age of 70. Okay, so at the age of 70, they want to have $750,000. How much do they need to save each month starting 1 month from now if the interest rate is 0.5%? So not a high yield, but it's not a high risk, right? So think about it in terms of risk. 0.5% interest is a really secure way to put my money in. It's not volatile like the market because I've only got 20 years to save this $750,000 that I want. So obviously this person didn't start thinking about retirement until they were already 50, but now they want to get some bank. How do they do that? Well, what I can say is that I am going to be looking for an unknown value of that's going to give me a future amount of $750,000 over a period of 240 months. Talk about this in a second. An interest rate of 0.5%. Because what did they give me? They gave me an N was equal to 20 years, but my deposits were taking place monthly. I wanted to know monthly deposits. So that means I need to change that N into years. So I'm going to do 20 times 12, which gives me 240. So 240 periods, monthly amount, interest rate of 0.5%, and the future value is known because that's the $750,000 that I want. What formula do I use? I'm going to use a generic formula that the annuity is equal to that future value multiplied by the A given F factor as a factor of interest and time. In this problem, that translates to $750,000 times A given F factor at 0.5% interest over 240 months. And so I looked that up on my compound interest table, and I that it's $750,000 on 6. And so that means the individual needs to save $1,620 every month. So you think about that. They're getting a paycheck, and maybe they're paid monthly, maybe they're paid bi-weekly, but every month they're going to put away $1,620 into the bank, and it's a guaranteed return of 5% per month, and they're just going to keep doing that for the next 20 years, but they will be able to withdraw they'll be able to draw $750,000. Now, a follow-up question to that problem would then be, if the person lived to 90, how much could they take out each month if they were increasing the return on their investment to maybe 3.25%? You see how we could figure that out? Then we would have a present value, we would have another N to work with, and we'd have a new interest rate to work with. And we could calculate that problem just as easily as we did this one. So, last problem. This one says a football coach receives his contract buyout of $7.5 million in monthly installments. 7.5 million is a little more than 750, isn't it? 1,000 there. So monthly installments over the next 4 years. So they bought him out at $7.5 million. But if the interest rate is 1% a month, how much does the coach receive at the end of each month? Well, again, we're looking at our interest rate is 1% a month, and our annuity is going to be in monthly installments. And so our N, instead of being 4 years, needs to be 48 months. So my interest is in months, my annuity is in months, my N is in months. We'll talk about more of this next week, but this is a real critical factor here. And we know the present value of the money. The present value of the money is $7.5 million. So I have that $7.5 million that I'm going to pay out over the next 48 months at an interest rate of 1%. Cash flow diagram. Well, they have the present value of $7.5 million. Coach is getting equal annualized payments over the next 48 months. So N equals 48 months at an interest rate of 1% a month. And we're going to find out how much those payments are. So A is the question mark. I have a present value, I know my interest rate, and I know my N. So baseline formula, what do I usually work with? A is equal to P times an A given P factor, which is a factor of the interest rate and of the timeline, N. So A is equal to $7,500,000, I'll write fully out this time, times A given P for an interest rate of 1% over 48 months. That's what I'm going to look up in my compound interest table. So I'm going to go to the 1% compound interest table, look for the A and P factor at time equals N equals 48. And my compound interest table will give me 0.0263, which multiplied out means that Coach is getting $197,250 a month. No one's really feeling bad for Coach right now because that's more than some people spend on their house, and he's getting that monthly for the next 4 years. But that's how his actual $7.5 million buyout looks like in monthly installments. All right, so take your quiz, study your formulas, and keep an eye on your email so that I can tell you where we will be meeting next. And then I thank you all very much and look forward to seeing you again soon.